where Thomas left off. So this is based on joint work with Thomas, and it's all in our recent paper called Trialities of W-algebras, except that it also uses some ideas from some of our previous papers, and those are referenced there. Okay, so I'll start by stating a main result, and then most of the talk will be an overview of the various ingredients involved in the proof. And then if I have enough time, I'll do a worked example. Otherwise, I'll pick up with this worked example on Wednesday. Okay, so the main result, let's say G is a simple finite dimensional Lie superalgebra or Lie algebra. And let F in G be a nilpotent element. So we can complete F to an SL2 triple in G. And the centralizer of this SL2, I'll call A. This is going to correspond to the affine sub-VOA of the corresponding W algebra. So we have the W algebra WKGF that Thomas just introduced, and there's some shift in level. So he wrote down an explicit formula for it. I'm just going to call it K prime. It depends on various theoretic data. So the affine sub-VOA of this W algebra will be VK prime A. A is some Lie sub-super algebra. The first theorem is let G be some reductive group of automorphisms of the W algebra. Then the orbifold here means G invariant subalgebra. There's always a vertex subalgebra. That is strongly finitely generated as a one parameter vertex algebra. And in particular, for generic values of K, it's strongly finitely generated. So I should say a few words about this. So we don't actually know the automorphism group of W algebras in general. We know that there's a big group of inner automorphisms that come from this Lie algebra A. So this Lie algebra A, you can exponentiate it. You get some reductive, some Lie group that will act. At least you can exponentiate the even part of it. So you get a big Lie group of inner automorphisms, but then there's also outer automorphisms. And I don't think we know all the outer automorphisms of W algebras. So for type A principal W algebras, we know there's a Z2 action. There are some examples where the outer automorphism group is infinite. But even though we don't know what the automorphism group is, we can still make this conclusion. The second theorem has to do with cosets of W algebras. So Thomas mentioned this, that if you have a VOA and you have a sub-VOA, the coset of the small VOA inside the big one is the subspace that commutes with everything in the small VOA, and that's always another vertex algebra. And so the cosets that I'm going to look at are going to be so-called affine cosets. So let's say that B is a reductive Lie subalgebra of A. So A might be a Lie superalgebra. So this is a Lie algebra, and reductive just means that it's a sum of abelian pieces and simple pieces. And then there will be a corresponding affine subalgebra, VLB, of the affine subalgebra of the full W algebra. And we can consider the coset. So this COM of VLB inside the W algebra means everything that commutes with this affine subalgebra. That's also strongly finitely generated as a one parameter algebra. So these are very general results. I'm going to outline how one proves these in general. In general, it's hard to make these arguments constructive. What is really useful is the examples that we care about that we'll need for the proof of our triality theorems. To be very explicit about what the generating types of these cosets are. And in that case, the invariant theory is nice enough that we can make this constructive. Okay, so the outline of the proof, let me say a few words about this before we get started with it. So first of all, the way you should think of these theorems is they are analogs of Hilbert's theorem that for a reductive group and a finite dimensional G module V, the ring of invariant polynomial functions is finitely generated. So these are analogs of this result of Hilbert, and there are some ideas from invariant theory that will be used in this proof. So the proof is based on various connections between vertex algebras and commutative algebra that I'll talk a little bit about more generally. So the first thing is that there are some well-known functors from vertex algebra to commutative rings. There's Joux's commutative algebra, which is somehow too small for our purposes. And it sits inside something bigger, which you get from taking Lie's canonical filtration. Any vertex algebra has its filtration. You can take the associated graded algebra. That's a differential commutative ring, and it contains the Joux's commutative algebra as the degree 0 part. So these are ways of getting commutative algebras for vertex algebras. And then the vertex algebra Hilbert theorem, or Hilbert problem for free field algebras. This is going to be occupy a good bit of the talk. So what this says is that for free field algebras, if you take a reductive group and you take the invariance in free field algebra, it's always strongly finitely generated. And these are the same free field algebras that Thomas talked about in his talk. And how is this done? Well, this involves passage to the associated graded algebra and using some ideas from commutative algebra and in particular from invariant theory in conjunction with ideas from vertex algebras and their representations. So this will take care of the problem for free field algebras. And then, as Thomas proved in his talk, W-algebras have the property that their limits are free field algebras. And so we will be able to pass from the result for free field algebras to the result for W-algebras. Okay, so this will work for orbifolds, and there will be a similar result for cosets. That's the result for cosets is actually more important for our purposes. Okay, so this is the overview. So let me first talk about the functors from vertex algebras to commutative algebras. So the first one is, this appeared in Zhu's thesis. Given a vertex algebra V, we can consider the space, I'm going to call it CV. It's spanned by elements of the form A minus 2 product B. And so A minus 2 product B is just the normal ordered product of the derivative of A. This is ddz in the, with respect to the formal variable z. It's the same as the translation operator. So normal ordered product of derivative of A with B for any A and B and V. So basically this is the space that's spanned by things where there's at least one derivative. And then I can take the vector space quotient, R sub V is V mod C of V. And this quotient space has a commutative ring structure. And so I'll denote the image of an element of V by A bar. A is in V, A bar is the image in this quotient. Okay, this should not be R of V, this means R sub V, that's a typo. So RV has a commutative associative product that's induced by the normal ordered product or Wick product. So I just take the product of A and B in the vertex algebra, I take the bar, you check this as independent of representative, and because of some basic identities in VOAs, this is commutative and associative. The identity element, the vacuum corresponds to the unit element. So we get a nice commutative ring. And it has actually more structure. It's a Poisson algebra. And I can take this zeroth product and take the bar of that. This gives me the Poisson bracket in this ring. Sometimes this Poisson bracket is trivial and you can go to a non-trivial one. You can take a higher product and make it non-trivial. So it's well known that strong generators for a vertex algebra give rise to generators for RV. This is one reason why strong generators are good to work with. And in fact, if V is freely generated by some subset of fields, so not only strongly, but we have a PPW basis of monomials in these elements, then, well, that means in particular that the VOA is linearly isomorphic to a big polynomial algebra on all these things and their derivatives. And then RV will be just isomorphic to the polynomial algebra on these elements. So V is freely generated, then RV is a polynomial ring. And so we have some basic examples of freely generated vertex algebras, all free field algebras, all affine VOAs, and all W algebras. And when I say freely generated, I mean in the super sense that odd fields will give rise to an exterior algebra, even fields will give rise to a polynomial algebra. So it's a super polynomial algebra. In general, RV is not a polynomial ring. It can be very complicated to describe this in general if the VOA is not freely generated. Okay, so as I said, this sits inside a bigger structure. So for any vertex algebra, we have Lee's canonical decreasing filtration. So FO contains F1, which contains F2, et cetera. So this is decreasing. The pth filtered piece, you can think of as the piece which is spanned by normal ordered products of things in the VOA such that the number of derivatives appearing is at least p. Okay, so here this one has n1 derivatives, n2 derivatives, et cetera. There are at least p derivatives in total. Okay, so clearly FO, things that have at least 0 derivatives, there's no condition, that's the whole vertex algebra. And also if you take apply the derivative to the pth filtered piece, you land inside the p+1 filtered piece. Okay, so the associated graded algebra is just the direct sum of FP mod FP+1. And you have a projection map that sends the pth filtered piece to its image in the associated graded algebra. Okay, so this associated graded is always a differential commutative graded ring. So again, this follows from basic identities in VOA. If you write down the commutator, normal ordered commutator, you see that it's written in terms of higher derivatives, and same thing for associators. So if A and B are in the pth and qth filtered piece respectively, then you can multiply the elements. So this lives in the sigma PA lives in the pth graded piece. This is in the qth graded piece. What I do is I take their Wick product and then I project to the p plus qth graded piece. So this is how you multiply things. And also the derivative, if you have something in the pth piece, you take the derivative in the VOA and then you project to the p plus 1th piece. So this gets the structure of a differential graded ring. Notice that this F1 was exactly this C of V that Zhu defined. This is the stuff with at least one derivative. So FO mod F1, this is the 0th graded piece. That's a copy of Zhu's commutative ring. And just like, so it turns out that Zhu's commutative ring, namely the 0th graded piece, this generates the graded algebra as a differential algebra. So in other words, if you take everything in Zhu's commutative algebra and then all the derivatives, that generates the whole algebra. So in particular, if the algebra is strongly generated by some elements, then the images in the graded algebra will generate the graded algebra as a differential ring. And it has more structure, just like the Zhu's commutative ring. It has a vertex Poisson structure, which I'll make use of later. I won't necessarily talk about it very explicitly, but it's an important ingredient in some of the things that we'll do, which is just induced by the vertex operations, the nth product for n greater than or equal to 0 on the vertex algebra. And this extends the Poisson structure on RV. Okay, so this is a bigger ring, and it's associated, a bigger ring that we can attach naturally to a VOA. And basically, this is very difficult to understand, except in the cases when V is strongly generated by some fields. So if V is freely generated, rather, if V is freely generated by some fields, then the graded algebra is just the polynomial ring on these things and all their derivatives. And so this holds for free field algebras, affine algebras, universal affine algebras, and universal W-algebras. If V is strongly but not freely generated by some fields, then the graded algebra is generated by those things mod some ideal. And this I is very difficult to describe in general. There are only a few examples where it can be described. So the philosophy in this talk is that if we know the structure of the graded algebra, so maybe it comes from a free field algebra and that we know that it's a differential polynomial ring, or somehow we know it for other reasons, then it allows V to be studied using tools from commutative algebra. Another thing that I'll mention without being very explicit about it is that many VOAs have different filtrations that give rise to the same associated graded algebra. So this Lee's canonical filtration is a decreasing filtration, but often they have increasing filtrations. And sometimes it's more convenient to use other filtrations and we get the same result in the end. But some things are easily stated in terms of, more easily stated in terms of other filtrations. So for example, for affine algebras, it's often convenient to take the filtration by the total length of a monomial in the generators and their derivatives rather than counting the number of derivatives. Okay. So those are, this will be an important functor for us. And let me now state the vertex algebra Hilbert problem. Okay, so let's say V is a vertex algebra which is strongly finitely generated. So that means that it's strongly generated by finitely many fields, or it can be. You can find finitely many fields that strongly generate it, not necessarily freely. And let's say that G is a reductive group of automorphisms of V. So a question is whether the orbifold or G invariant vertex algebra is also strongly finitely generated. So I'm going to call this the vertex algebra Hilbert problem because of its analogy with classical questions in invariant theory of finite generation of invariant rings. So in general, the answer turns out to be no. And what I'm going to do, we can't prove this in general. We're going to prove it for a class of algebras that includes W-algebras and affine algebras and such things. But before I talk about this in even this setting of things like W-algebras, somewhat general setting, I want to give you two examples to illustrate this phenomenon, how it can fail and how it cannot fail. to give you some sense of how the proof might go and also why such things happen. It's a little bit of a strange phenomenon because vertex algebras are not Noetherian. So the reason why this happens is not exactly for classical reasons. It actually depends very sensitively on the fact that VOAs are non-associative. Okay, so let me start with the degenerate Heisenberg algebra of rank 1. So what is this thing? I'm going to call it H tilde. So degenerate Heisenberg algebra just means that it's, this is an algebra with one generator. We'll say that it has weight 1. There's no Virasoro structure, so I have a grading, but I don't have an actual Virasoro algebra. So it's, it has one field which commutes with itself. That's why this is degenerate. If this thing had a second order pole with itself, that would be the non-degenerate Heisenberg. That's the one that we're going to do next. This is the degenerate one. So there's one field. So what does H tilde look like as a vertex algebra? Well, at least as a vector space, and also as a vertex algebra, it's just the differential polynomial algebra on alpha, derivative alpha, second derivative alpha, etc. So it's free abelian vertex algebra with one generator, and it's commutative and associative. Okay, so it has a Z2 action. So we're going to look at the orbifold under Z2. What does Z2 do? Well, the non-trivial element, the involution, sends alpha to minus alpha. And there's no OPEs to preserve, so this is obviously an automorphism of this. There's nothing really to say. It's an automorphism of the vector space. And we want it to be compatible with this derivative operation delta. And to be an automorphism of the vertex algebra, that's a requirement that it's compatible with delta. So it should be also stated that the theta of kth derivative alpha is minus kth derivative alpha for all k. Okay, so that determines the automorphism on the generators, and then it extends to everything. Okay, so it's easy to see what the Z2 invariants are, at least from a certain perspective. It's simply spanned by all the monomials. So first of all, this is an abelian group action. It acts diagonalizably, so invariants are generated by monomials. And what monomials are there? They're even degree monomials. So all the products of various derivatives, I don't care what the derivatives are, I just care that the total number is even. All such monomials, the span of them will be the Z2 invariants. So I'm trying to whittle this down and find a more and more economical generating sets. So if I only want even degree things, I may as well just take my quadratics. Everything of even degree could be generated by quadratics. So let me call these things Qij. This is just ith derivative of alpha times jth derivative of alpha. And in fact, I don't need to take all Qij's because Qij is the same thing as Qji. So I can say that I is greater than or equal to j. Okay, so strong generators for an abelian vertex algebra are the same thing as generators as a differential graded ring. Okay, so there's certain redundancies. Well, I got rid of some redundancy by saying that the I is greater than or equal to j, but there's also some redundancy in the sense of differential algebras because there are certain linear relations between these things and their derivatives. So if I take the derivative of Qij, this derivative is a derivation. So what does it do? It takes del I alpha to del I plus 1 alpha. So when I apply this and I use the Leibniz rule, I get Qi plus 1j plus Qij plus 1. So this is a linear relation. It says that I don't need both of these two because one of them can be obtained from the other by adding to it or subtracting a derivative. So if I only want differential algebra generators, I can get rid of some of these. And so if you play with this a little bit, it's easy to see that kind of most economical choice is that I take the things that look like Q2n 0. So I take a 0 for the second entry, and the first one is even. And I take all derivatives of those. Okay, so that turns out to be enough to span. If I take the span of all the derivatives of the Q2n zeros, I get the same as the span of the Qij's. And if over here, if I take I greater equal to j, or if I take k and n arbitrary, these sets are linearly independent and they span the same space. So that means that this smaller set, just the Q2n zeros, is sufficient to strongly generate my orbifold or generate it as a differential algebra. Because I can take all the derivatives and then I can take linear combinations, then I get all these Q's, and then I multiply them, I get all the even degree things. Okay, so I claim that this set, these Q2n zeros are actually a minimal strong generating set. So if I throw any of them out, I no longer have enough to generate And in particular, this is not a strongly finitely generated vertex algebra. Okay? So, and it doesn't matter whether I pick a different generating set, the same phenomenon holds. So how do you see this? Well, first of all, I just told you that these were independent. It's a quick check to see that these are linearly independent. So they're definitely not algebraically independent. And there's now a question of whether you can use algebraic relations to get rid of some of these. Well, it turns out that you can't. So all the algebraic relations, it's easier to express them in terms of the original generating set Qij. And they look like these 2x2 determinants. So Qij, Qkl minus Qil, Qkj. You know, if you go back to what these look like, it's obvious that you can move things around and that's a relation. It's not very difficult to see that that generates all the relations. This is actually a special case of one of the fundamental theorems of invariant theory for the orthogonal group, On in the case of O1. O1 is just Z2. Okay, so these generate the relations. And these relations are homogeneous of degree 2 in these variables. So that means that anything which is a consequence of these relations cannot have a linear term. So there are no more linear terms that you can eliminate. Therefore, this set is minimal. Okay, so the purpose of this was to show you an example where you have a nice, strongly finitely generated vertex algebra, this H tilde, it has one generator. But the orbifold under the simplest group that you can imagine, Z2, is not strongly finitely generated. Okay, more generally, it turns out that if you have any differential polynomial algebra, say starting with finitely many vectors, take a finite dimensional vector space, take the corresponding differential polynomial algebra, take a finite group action, take the invariant, it's never finitely generated as a differential ring. Okay, so why is it that such things can happen for vertex algebras? Well, it's quite subtle, so I want to give you an example. And this example is the non-degenerate Heisenberg algebra. So the only difference is that my even field that strongly generates it now has the second order pole. Okay? And so again, this Heisenberg algebra of rank 1 has a basis consisting of normally ordered monomials in the generators and their derivatives. So it's very similar to the degenerate one, except that I have to take Wick product because if I reorder things, this is not a commutative product anymore or an associative product. So I have to be a little bit more careful, but at least as a vector space, these are all the same. H is the same as H tilde, which is the same as the associated gradient of H. And that's just the differential polynomial algebra on one generator, its derivatives. So it turns out that the full automorphism group of H is Z2. And what does it do? It sends alpha to minus alpha, just like before. And then also it sends the kth derivative of alpha to the kth derivative of minus the kth derivative of alpha. So the action of Z2 looks the same. Everything looks the same, except that we have the second order pole now. Okay, so just like before, the Z2 orbifold is spanned by all the normally ordered monomials that have even degree. So it looks the same as before. It's linearly isomorphic to the previous one, except that these are normally ordered monomials. So we have linear isomorphism between HZ2 and tilde HZ2. And again, this requires a small induction on degree, but it's not very difficult to see that these monomials are generated by the quadratics, but now it's a normally ordered quadratic. So if you write down some product, normal ordered product of these quadratics, the leading term will be the same thing if I didn't have normal order, but then there's subleading terms that you have to worry about, but then you can keep going. So by induction and degree, it's easy to see that the quadratics are enough. Just like before, omega ij is the same as omega ji, so I can throw out some of them. There's also some redundancy because of these relations between a derivative and things at the next level, so I can throw some out. And just like before, a convenient set to take is the kth derivative of the omega 2n zeros. So the span of these guys is the same as the span of the omega ij's. These things are linearly independent, they span the same space. So by the same, everything so far is the same, we get that the set of omega 2n zeros is a strong generating set for this orbifold. But this is the point of departure, where these two examples become very different from each other, because there's a well-known theorem of Dong and Nagatomo from 1999 that HZ2 actually has a minimal strong generating set consisting of just the first two. I only need omega 0, 0 and omega 2, 0. Okay, so I don't need any of the higher ones. So we say that it's of type W24. This means that it has minimal strong generating set consisting of a field in weight 2 and a field in weight 4. This one, because alpha had weight 1, omega 0, 0 is alpha times alpha, that's got weight 2. This one is second derivative alpha times alpha, that's got weight 4. Okay, so it turns out that, so I think that they probably stated this slightly differently. You can, this W omega 2, 0 is not primary with respect to this Virasoro. Actually, this isn't even a Virasoro. You have to rescale it by a half to make it a Virasoro. So you can replace this with a primary field. It turns out this algebra is isomorphic to a W-algebra of SO5 or SP4 with central charge 1. There's various nice things you can say about this example. But I'm going to actually outline a proof of this statement. It's not the same as the proof that's in original proof due to Dong and Nagatomo, but I'm going to outline a proof that generalizes in a certain sense to the examples that we need and also illustrates why this happens. So what we have to do to show that these two fields generate is we have to show that all the higher ones, namely omega 4, 0, omega 6, 0, et cetera, they can all be written as normally ordered polynomials in these two and their derivatives. So we have to write down some relations that express them that way. And so the main observation, sort of the philosophy between why this can happen, is that because of the non-associativity of this Wick product or normal ordered product, if you write down an expression that corresponds to a classical relation between the Qs. In the previous slide, I said that Qij, Qkl minus Qil, Qkj is 0. So this is obviously 0. So if you soup this up and replace the Qs with the omegas, replace the product with the normal ordered product, this is not 0 anymore because of non-associativity. The leading term, which is degree 4 in the Heisenberg generator and its derivatives, that's going to go away. But there's a subleading term, which is degree 2, that survives. And that's because of non-associativity. The reason this doesn't happen for H tilde is because we do have associativity. So let me write down one example. So in fact, it's easy to write down the general formula for what this difference should be, but I'm only going to write it down for the minimal weight relation, which has weight 6. So let's take the relation Q00, Q11 minus Q10, Q10. This is weight 6 because this is weight 2 and this is weight 4. Okay, so this is 0 in the graded algebra or in the H tilde, but it's not 0 in the Heisenberg algebra. And if you write this down, the correction I've written down in terms of our omegas on the right side, it's 7/6 omega 3,1 minus 1/12 omega 4,0. And you get this just from VOA axioms and OPE algebra and the Heisenberg algebra. Okay, so I want to rewrite this in some way that's more enlightening. So remember that I prefer to use as my generating set the Q 2n zeros. So I want to write everything in terms of those variables. So this 1, 1, I mentioned earlier that the span of all the omegas is the same as the span of the omega 2n zeros and their derivatives. So I know that, well, this has weight 4. So I have to be able to write it in terms of second derivative of omega 0, 0 and just omega 2, 0. And this is the way that you write it. There's a 1/2 and a -1 as my coefficients. And similarly, omega 3,1 is minus omega 4,0 plus something times second derivative of 2, 0 and something times fourth derivative of 0, 0. This is just using the linear isomorphism between these two spanning sets to do this replacement. So now what I'm going to do is I'm going to take this entire relation. Whenever I see something that's not one of the generators that I like, so this 1, 1 I don't want, I want to replace it. I also want to replace 0, 1 with the derivative of 0, 0. I want to replace 3, 1 with this expression. So I do all these replacements, and then I solve for omega 4, 0. So I have some 4 zeros on this side. I also pick some up from here. And thankfully, they don't cancel. And I'm left with some 0, 4. This should say 4, 0, not 0, 4. I messed that up. And same thing here. This should say 2, 0. I'll correct these typos. But the point is that you're able to write omega 4, 0, the thing that you're trying to eliminate, as a normally ordered polynomial in the 0, 0 and 2, 0. There's some way to do this. This could never happen in the commutative ring because all the relations are homogeneous degree 2, but in the VOA, because of non-associativity, you can get these linear corrections when this happens. Okay, so in general, we call this a decoupling relation, since this omega 4, 0 can be written as a normally ordered expression in these two and their derivatives. And that means that we don't need it in our strong generating set. And similarly, I can start from this relation and then apply this operator, omega 2, 0, first product. This is a product which raises conformal weight by 2. I apply it to that relation and then I back substitute and I keep doing this. So recursively, you can construct all these higher relations. They get very complicated. The one for omega 6, 0 is now degree 6 in the Heisenberg fields, and they get much longer and more complicated after you do this substitution. But there's a straightforward procedure for constructing all this. And so that completes the proof that these two suffice to strongly generate the Z2 orbifold. I've eliminated all the other ones. I knew that a strong generating set consisted of all the omega 2 and zeros, and I only need these two. And then the fact that this is minimal is pretty easy to prove too, that once you write down normal ordered polynomials in these two, there are no relations in weight less than 8. In weight 8, you have a relation. So in particular, there are no relations in weight 4 or 2, so you can't possibly eliminate one of those. Okay, so that's a complete proof of Dong and Nagatomo's theorem. And it more or less illustrates this phenomenon, right? So somehow when you can have two VOAs that have the same vector space structure. They look rather similar, but one of them is strongly finitely generated and one of them is not. So I don't actually know what good criteria should be for the Vertex algebra Hilbert problem to work in general. So in this example, it suggests that maybe simplicity is a good thing to impose, but that's actually too strong. So for abelian vertex algebras, it usually fails, but there are examples of VOAs that are not simple where it works. So in general, I don't know, but I want to explain how this goes for free field algebras. Okay, so I'm going to remind you of the free field algebras that were introduced in Thomas's talk, but I'm going to sort of write down slightly different notation for them, explicit notation, because I'm going to come back to these later. So there are 4 families of free field algebras. There are the ones that I'll call even of orthogonal type. So even of orthogonal type means that the generators are even and the poles are even. So it's either a second order pole, fourth order pole, sixth order pole, etc. And the generators are going to be, they'll have weight k over 2. And the OPE relation looks just like the Heisenberg relation, except that this k might not be a 2, it might be 4 or 6, etc. So when k is 2, then O even n k is 2, this is the usual rank n Heisenberg algebra. And so all of them, as Thomas mentioned, can be realized inside the Heisenberg algebra. If you take standard generators for the Heisenberg algebra, I just take the derivatives of order k over 2 minus 1, and then I have to rescale them by some factor to make it so the OPE comes out exactly like this, rather than with some signs. Okay, the important property that O even nk has is that, well, it has no conformal vector unless k is 2. So it's not a vertex operator algebra in general, but it's always simple. That means it has no non-trivial ideals. And its full automorphism group is the orthogonal group. Just like for the Heisenberg algebra, being an automorphism of the vertex algebra means that you preserve the span of the generators and you preserve a symmetric non-degenerate bilinear form. That's the same thing as being an orthogonal group. Okay, so then we have even algebras of symplectic type. So here the generators are even, but the poles are odd. And so in this case, you have to have the number of generators is even. So I'm going to sort of pick a symplectic basis, pick n, a1 through an, and then b1 through bn. The a's commute with themselves, the b's commute, and the a's and the b's have this non-trivial pairing. And you pick up a sign if you change the order. And so when k is 1, this is the usual symplectic bosons or beta-gamma system of rank n. And you can realize for higher k's, if k is 3 or 5 or 7 or whatever, you can realize them inside the beta-gamma system by taking the derivatives of the standard generators of the appropriate order. And again, it has no conformal vector if k is bigger than 1, but it's always simple. And the full automorphism group is a symplectic group. So just like the beta-gamma system, when you say that the generators have weight 1/2, the automorphism group is the symplectic group. This is a symplectic space, C2n. The same thing holds here. So preserving these OPEs means preserving a symplectic form. Okay, so then we've got odd algebras of orthogonal type. So here the generators are odd, the poles are also odd. And when K is 1, these algebras are just the rank n free fermion algebra. So when K is 1, you have a first order pole. That's what the free fermion algebra usually looks like. All the higher ones can be realized inside the free fermion algebra by taking derivatives of the generators. Again, there's no conformal vector for K bigger than 1, but this algebra is simple, and it's got full homomorphism group ON. For the same reason that the orthogonal group is the automorphism group of Fn. We just have to preserve a non-degenerate symmetric form. And then lastly, there's odd algebras of symplectic type, and I'll call them S odd NK. So N is the rank, K is this sort of height. Here the poles are even, the generators are odd. And this one generalizes the symplectic fermion algebra that Thomas talked about. If N is 2, we get the symplectic fermion algebra. Again, we can realize them inside symplectic fermion algebra. And they don't typically have conformal structures, but they're simple, and the automorphism group is the symplectic group. So the thing to take away from this is we're going to study orbifolds of all these free field algebras. It's important to know what the parity is and what the full automorphism group is. And so the parity could be either even or odd. The automorphism group could be either symplectic or orthogonal. That characterizes all of these algebras. Okay. So the main theorem here is that, let's say V is a vertex algebra that can be written as a tensor product of these free field algebras. Each of these VIs is one of these free field algebras. So finite tensor products of these. And let's say that G is a reductive group of automorphisms of V, any reductive group of automorphisms. Then VG is strongly finitely generated. So this is a vast generalization of what we just saw for the Heisenberg algebra. That's the case where this tensor product has only one factor, and that one factor is an O even 1, 2. Okay, so it's a very baby case of this theorem. So of course you can't prove this in the way that we proved it for the Heisenberg algebra explicitly, because that required us to know the generators for the invariants and the relations. That's not something that we know for a general group. So we have to find some other ways of dealing with this. So I'm going to actually spend some time outlining the proof and what the steps are. So the first observation is that suppose I have two of these factors that are of the same type. So when I say the same type, it means that it's either an O or an S, and even or odd, and also the K is the same. So if Ks are different, then I don't call them the same type. But if O even NK and O even MK, I say, are of the same type. Then I can combine those into a single algebra of this type, because O even NK, tensor O even MK, is isomorphic to O even N plus MK. Okay, and same thing for the other types. So without loss of generality, I can assume that in this factorization, the types are distinct. Why do I want to do this? Well, because the types are distinct, G is by definition an automorphism of this vertex algebra, or group of automorphisms. So it has to preserve the weight and the parity of generators. And which type you're in is determined completely by the weight and the parity of the generators. So that means that G has to act on these factors separately. It has to actually be a subgroup of this product of automorphism groups for these factors. Okay, so that means that it's a subgroup of a product of these GIs, and each of these GIs is either an orthogonal group or a symplectic group. Okay, so this is a useful observation. So the first step is I'm going to reduce to the case where V is just one of these free field algebras. So that means that my factorization has only one factor. And also G is the full automorphism group. So that means it's either an orthogonal group or a symplectic group. So I'm going to do that case first and then go from there. And why is it that this case you can handle? Well, it's because the associated graded algebra is either a symmetric or exterior algebra on the direct sum of many copies of the vector space VI, which is the standard module for this aught V. So what do I mean by this? For example, let's say that I'm talking about O even NK. So, or let's say O even N2, N Heisenbergs. So how many generators are there's N of them. So think of this as a copy of Cn, the standard module for On. Then I've got the derivatives of those. That's like the next copy of Cn, and then the second derivatives of the next copy, et cetera. When I pass to the associated graded algebra, I take the direct sum of all the spaces. Which one I'm in depends on how many derivatives I have. And then I take the symmetric algebra on that for O even. And if it was one of the odd ones, it would be an exterior algebra. Okay, so I passed to the associated graded. This is where I use the thing I mentioned earlier that you should pass to the associated graded. This becomes a nice commutative ring. In this case, it is a symmetric algebra or exterior algebra and such things. And there is a way of dealing with the invariant theory in a ring of this form, either symmetric or exterior algebra, or even tensor algebra on a sum of copies of the standard representation of a classical group. So this is Weil's first and second fundamental theorems of invariant theory. So with that first fundamental theorem of invariant theory is a description of the generators for such a ring of invariants. And second fundamental theorem is the relations. And so we need both of these. So I'm going to explain roughly how this goes for Hn. And this is, think of this as the natural generalization of Dong-Nagatomo's result for one Heisenberg. That was the case where n is 1. So let's look at how this goes for the rank n Heisenberg algebra, O even n2. So as I said, it's got n generators, alpha 1 through alpha n, and they satisfy these OPE relations. You have second order pole when I equals j. So if you pass to the associated graded algebra, then I get polynomials in the sum of many copies of Cn. The first fundamental theorem of invariant theory for On says that in such a ring, the generators are quadratic and they correspond to the pairing between two different copies, the pairing being symmetric. I mean, the pairing it comes from the bilinear form, so this pairing will then be invariant because On preserves this pairing. So when I say the del A and del B, this means sort of the eighth copy with A derivatives. This is the bth copy with B derivatives. I write down this sum, and this is exactly what I had for one Heisenberg, except that this sum only went from I equals 1 to 1. When it goes from I equals 1 to n, that's the analog for n Heisenberg algebras. So the generators look very similar to the case that we talked about before. The relations also look similar. So in the classical invariant ring, the relations are n plus 1 by n plus 1 determinants in the generators. So this thing that I wrote down before, this Qij, Qkl minus the switch, that was a 2 by 2 determinant. The relation in n copies is an n plus 1 by n plus 1 determinants in these generators. And which ones you have are indexed by some, I take a list, I'll call it big I, of entries that go in the first slot, and then a list that go in the second slot. The i's have to be strictly increasing and the j's have to be strictly increasing. This determinant classically is what a relation looks like. So that would normally vanish. But then in the Vertex algebra, that, just like for the case of one Heisenberg, that thing didn't vanish, but it had some corrections, and you can keep correcting to make it vanish. The leading term looks like this determinant. And we get that from the passage to the associated graded together with invariant theory for the orthogonal group. Okay, so that's what the relations are complicated, but the leading term is the determinant. These things correspond to classical relations, but because of non-associativity, the determinant doesn't actually vanish. So it requires corrections in all lower degrees. So for one Heisenberg, we only had to go to one lower degree. There was no room for anything more. So here, this determinant is degree n plus 1 in the generators. So in degree n minus 1, degree n minus 2, all the way down to degree 1, we need corrections. And these corrections, in general, will depend on the choice of normal ordering. So when I write down this normal order determinant, it's not completely well defined because my normal ordering, I have to make a choice of the order of multiplying and also the associativity. So, and then all my corrections will be normal ordered things that have some choices that I can make. So a lot of things in the correction are not very canonical. But it turns out there's a certain term which is canonical, which is the only one that we actually care about. And so what I should, to illustrate this, I should think of just like for one copy of the Heisenberg, I should think of replacing the generators, the omega ij's that I had written down here, with things like the kth derivative of omega 2k0. Sorry, this shouldn't be 2k, this should be 2n. The k has to be different from n. Okay, so this is a better choice. And just like with one Heisenberg, these things will generate. This will be a strong generating set. And what you have to do is, well, first notice that this Dij has conformal weight Well, the sum of all the derivatives that I have is, this means the sum of the entries of the I slot, the sum of the entries of the J, and then plus 2n plus 2, because the degree in the Heisenberg fields is 2n plus 2. So that's what the weight of this determinant is. Let's say that the weight is even. If it's even, then there will be some, when you look at all the correction terms in the lowest degree, which is degree 1 in the generators, there will be this term omega w minus 2 comma 0. So w minus 2 is even. So this is one of my generating fields after changing to this better choice. And there will be some constant times that. This Rnij is a number that depends on I and j. And so I want to think of this as one of the correction terms. And so it must be proven that this particular correction term is independent of all my choices. This is not very difficult to show. So it's canonical, it's independent of all these things. And why is it important? What really matters is that this constant term Rnij, the coefficient of this is non-zero. If I could prove that this thing were non-zero, then I could move this to one side and solve for this. And then it's easy to see that everything else that appears in this Dij, together with its corrections, doesn't depend on this omega, it only depends on the lower ones. So what I would get would be a decoupling relation for this particular generator, omega w minus 2, 0. I could write it in terms of the others, just like I did for the rank 1 case, where we wrote w4, 0, or omega 4, 0 in terms of 0, 0, and 2, 0. That's exactly what we're trying to do here. And it only depends on this coefficient being non-zero. Just like in that example, it only depended on that, the coefficient of omega 4, 0 being non-zero. And so this is actually quite a difficult thing to prove. And so the best way that I know how to handle this is to write down a recursive formula that these things satisfy in terms of lower n's and also different i's and j's. And so you have to look at the totality of all these expressions for all n and consider some recursions that they satisfy to show this. But anyway, so this is what allows you to show that HNON is strongly finitely generated. You show that at some point these constants are non-zero, then you can eliminate something. And then just like in the case of H1 Heisenberg, once I have one decoupling relation, then I can easily construct all the higher ones by a bootstrap procedure. That also works here in the same way. Okay, so I only told you how this goes for HNON, but exactly the same thing works for the odd orthogonal ones and also the ones where the poles are higher. And the ones where it's odd orthogonal, the relations are determinants without signs. There's sort of fermionic determinants. And in the case where we work with the symplectic group, the relations are not determinants, they're Pfaffians. So you need the fundamental theorem of invariant theory for the symplectic group with its standard representation and it's the orthogonal group with its standard representation. So using that, you can handle all the cases where V is one of those algebras and the group is the full homomorphism group. So this is maybe the most difficult step, but that's I'll call that step 1. So far, so good? Okay, so step 1 is we understand what happens when V is one type, we understand when we have the full homomorphism group. Now we're going to work with just one type, but we're going to we have to understand something about the representation theory of this object, V ought V. So we're going to decompose, if I have a general group, we're going to decompose the orbifold for a general group as a module for this object. We need to know something about its representation theory. So the first thing is, as we get from step 1, that all these algebras, these V ought V's, have abelian Jus algebras. So the Jus algebra is an associative algebra that one can attach to a vertex algebra that is very good for studying its representation theory in the sense that there's a big class of modules for the vertex algebra, the ordinary modules, with the property that the irreducible ordinary modules for the VOA are in bijection with the irreducible modules for the Jus algebra. So this Jus algebra turns out to be abelian. That's very rarely the case, but if it is, it's very nice because it means that the irreducible ordinary modules for this vertex algebra are they have one-dimensional top components. So the modules for the Jus algebra are all one-dimensional, and they are parameterized by the point in the max spec of this commutative ring. So max spec of this commutative ring is some algebraic variety, and the maximum ideals here, the points will be in bijection with these modules. So this is useful. Another thing which is useful is that I can decompose the whole free field algebra. And remember, this V is of one type at the moment. It's either orthogonal, symplectic, even or odd. I can decompose it as a sum of a module for the odd V. So S is the set of irreducible finite dimensional modules for my group, which is either symplectic or orthogonal. And then MV are inequivalent irreducible modules for this orbifold, this V odd V. This is a multiplicity-free sum. So in other words, the multiplicity spaces for LV are exactly inequivalent irreducible modules for this VOA. Okay, this is a general theorem of Dongli-Mason that we can apply here. But the part of step 2, which is difficult, is that these modules have a special property that they're C1 cofinite. Okay, so let me just remind you what this means. So if I had a VOA V, say with a grade, let's say that this is it has a grading by weight. And this n could either be an integer or a half integer. If I have a module over such a VOA, we'll call it C1 cofinite. If the following subspace has finite codimension. So what I do is I take all the things where I take A minus 1 product M, where A lives in the positively graded part. So A can't be a constant. It can't be the vacuum. It can be anything positively graded. And M should be an M. I should say that the weight 0 part here is just the constants, just the field. So if I take this normal ordered product or the minus 1 product of anything in the module with positively graded things, I get a subspace. It may not be everything, but it's almost everything. That space has finite codimension. That's what I mean by C1 cofinite. So that is a very difficult thing to prove in this setting. So it's well known that if V is C2 cofinite, that means that Jou's commutative algebra is finite dimensional, then all these modules are C1 cofinite. But for a VOA that's not C2 cofinite, that's a difficult thing to prove. And so a major step in this program is to prove that all these modules have that property. Notice that I don't prove that all the V odd V modules are C1 cofinite, only the ones that appear in the decomposition of V. So there are some cases where we can prove it for all the modules, but I don't know how to show that in general. Turns out it's not necessary at this point. It would be a very important thing to prove, but we don't know how to do that. So, okay, so we have all these modules, they're C1 cofinite. Now the next step is that I want to, this is step 3. Now, again, V is one of these types, but G is now an arbitrary reductive group. So now I don't know anything about its invariant theory. So I can't easily, well, there's a little bit that I know that I'm going to use, but I don't know anything very explicit. So I can't hope to use an approach that's similar to the case of Dong-Nagatomo's theorem. But what I can do is decompose VG as a V odd V module, right? So G is a subgroup of odd V, so VG is an extension of V odd V. I can decompose it. It's going to be a sum of irreducible V odd V modules, which are C1 cofinite. I left out the word module here, but it's supposed to say module. Okay, and so in general, it's not a finite sum. So if the group is a finite group, then this will have only finitely many summands. But if the group is a, say, infinite compact Lie group, then that's not the case anymore. But what is always true is that V has a strong generating set that lies in the sum of only finitely many of these modules. Okay, so this is an important thing to prove. And this turns out to be a consequence of so-called Weil's theorem on polarization. So this is a famous result in invariant theory. I'm going to just state how this goes for the orthogonal even case, and then see how it applies over here. So first of all, if I take let's say I take O even NK. So this is the even orthogonal one. So the associated graded algebra is a symmetric algebra. It's a polynomial algebra on a bunch of copies of Cn. The Cn is the standard module for On. This is an isomorphism of On modules and of rings. So, right, the associated graded is just this polynomial algebra. So think of this, so this is the polynomials on this direct sum of copies of Vk. You can think of the direct sum only up to, say, p minus 1. That means I've got p copies. Think of this as the set of n by p matrices, where the orthogonal group is acting on the left. On the right, there's an action of GLP, right? And that commutes with the left action of On. So GLP, well, it acts on just p copies. And if I pass to the limit as p goes to infinity, I get GL infinity acting on this full direct sum. Okay, and it commutes with the action of G, so it actually acts, the action descends to the ring of invariance inside this symmetric algebra, which I'm going to call R. So the symmetric algebra is the same thing as the graded of the vertex algebra, and the G invariance I'm going to call R. Okay, so even though I don't really know much about what this looks like, I know that, well, there's an action of GLP on it, so this is useful. And so the elements of GL, sorry, there's an action of GLP for all p's, there's an action of GL infinity. The elements of GL infinity I'm going to call polarization operators. And given some element F and R, when I apply polarization to it, I just call that a polarization of F. And so here's Weil's theorem on polarizations, that R is generated by the polarizations of generators. If I only go up to n, I only need to have n copies of this vector space. Why do I need n? Well, that's the dimension of that vector space. This is n-dimensional. So if I take n copies of this, and I take just the invariants that appear here, that's obviously not the full invariant ring, but I can get the rest of it by applying polarization. So in other words, all the types of invariants you already see if you take the first n copies, and then the other ones are, they're of the same type, you can get them by polarizing. So this is a very strong result. And in particular, because G is reductive, if I just take finitely many copies, then this is a finitely generated ring. So that means that there exists a finite set, say F1 through Fr, whose polarizations generate R. R is not finitely generated, but it's generated by finitely many together with polarizations. Now, we have a linear isomorphism from R, which was the graded, if I first take the graded algebra and then take G invariance. So that commutes linearly with taking the, well, I can just take the G invariance. This is the orbifold that I want. Linearly, that's the same thing as R. And it turns out that these polarizations can be realized inside the action of this algebra O even NK ON. This is this orbifold under the full automorphism group. If you remember, we want to decompose the G orbifold as a module for this orbifold for the biggest group that you can. And the action of this realizes the polarization operators under this isomorphism. It's sort of a way of quantizing the polarization action. And so without loss of generality, I can replace these Fs with highest weight modules for these modules for the ON orbifold. Remember, I have a decomposition into these modules. I can, maybe I have to take more Fs, and maybe I have to replace F with the highest weight vector in the corresponding module, but I don't destroy the property that polarizations generate by doing that. So I can assume without loss of generality that these guys are highest weight modules in my decomposition. And then it is apparent that the orbifold is generated by F1 through Fn together with the action of this orbifold for the full automorphism group. And so now the theorem that I want, which is that the G orbifold is strongly finitely generated, this is a consequence of the C1 cofiniteness of these modules together with the fact that this orbifold for the ON, or the full automorphism group, is finitely generated, strongly finitely generated. So in other words, each of these modules is generated by an F. I have to consider it C1 space, right? I had that space and I take this, the quotient, and there were finitely many, that was finite dimensional. So I pick a basis for that space. Those things, for each one of those modules, I take a basis for that C1 space. Those together with the generators for this ON orbifold will be constructively my strong finite generating set. It may not be minimal. In fact, it typically is very far from minimal, but at least you can show somewhat constructively that this is the case. Constructively modulo this classical invariant problem, which is understanding the fundamental theorem of invariant theory for G. If G is general, we don't know anything about that. But if I did, then I could make this constructive. Okay, so that's how the story goes for a general G, but one flavor of free field algebras. So for the other flavors, it's exactly the same. Again, I have the C1 cofiniteness of modules. I have Weil's polarization theorem. I can do it the same way for each of these flavors. The very last step is, what if I have a general free field algebra that's a tensor product of a bunch of things? And now G is some reductive group. So the object that I want to work with to decompose this as a module over is the tensor product of these VI alt VIs. these are each objects of the kind that I've been studying, right? Each of these odd VIs is orthogonal or symplectic. These are all the things that I actually do have some good understanding of and their representation theory. All the modules for these pieces are C1 cofinite. I'm going to take this VG and decompose it as a module for this tensor product. Okay, so VG is certainly not the product of the invariants in each pieces. All I can say is that it's a module over the product of invariants for these VIs, these odd VIs. And as such, using violent polarization theory again, it has a strong generating set that lies in the sum of finitely many modules that are tensor products of these modules. They all have C1 cofiniteness property. Putting all this together, you get the result for VG. Okay? Any questions about this procedure? So I said this rather quickly, but the sort of takeaway is that we see how this works for H1. That story is basically the same for all the VI odd VIs with some difficulties because I have to deal with classical invariant theory for bigger groups, but essentially it's the same thing. And then the general story comes from decomposing as a module for these things and proving something about the representation theory of these VOAs, the VI odd VIs. Okay, so this is how the story goes for free field algebras. And unfortunately, it's very hard to generalize this and to try to do something similar in other settings, even for, say, affine VOAs. If you try to do it the same way, it's very difficult. We don't really have a good understanding of the invariants under the full automorphism group for affine VOAs. And it's much harder to study those algebras, and they do not have abelian Joux algebras. So anyway, there are ways, though, and so this is the theme that Thomas was talking about at the end, of passing from such a story to VOAs that have limits which are free field algebras. So let me say a few words about vertex algebras over commutative rings, and then we're going to apply this methodology. So I'm actually going to do two completely different things with VOAs over commutative rings. One I'll do today and one I'll do on Wednesday. So first of all, the fact that VOAs make sense over commutative rings with the identity element was observed from the very beginning of the subject by Borchertz. And people have worked with these in the past. People have constructed VOAs over the integers. For this talk, and also my talk on Wednesday, R will always be a finitely generated C algebra. So this is much easier than the general case. In the general case, if you say work with the integers, or in general work with a ring that doesn't have enough denominators, then there's some difficulty in defining the translation operator because you don't have enough denominators. So there's a paper of Mason where he develops the foundations of this in some generality, and he shows that there's a natural replacement for the translation operator called a Hasse-Schmidt derivation, which we don't have to worry about because we have enough denominators. We have a C algebra. So instead of being a vector space, a vertex algebra would be an R module. And all the operations, like I have these various vertex algebra products, they're not linear maps, but they're R module homomorphisms. And you can make, so you do everything with the language of R modules. You can define the OPEs, you can define the locality. Everything works the same way. We don't actually want to assume that V is a free R module, but often it happens that that's the case. So often, but not always, I'll assume that we have a Virasoro action. So it's supposed to be a field that satisfies the usual Virasoro relations. This C is now an element of my ring, not necessarily. Whatever this ring is, C is just an element of the ring. And we want LO to be diagonalizable, L-1 to act by this derivative, the translation operator. And the conformal weight grading should be an R module decomposition. So we don't assume, so these VNs are the weight graded pieces. VO, I want to assume is isomorphic to the ring. This is so-called CFT type. And all the examples that we'll consider that will be the case. And so these guys don't have to be, we don't assume that they're free modules, but we do want them to have a good notion of rank. So maybe assuming that their projective of finite rank is good enough so that we can define the rank. So sometimes it's convenient to talk about the character of these modules, and for that I need them to have a rank. And so one definition which is subtle and important is the notion of simplicity in this setting. So normally when we say that a vertex algebra is simple, it means it has no non-trivial ideals. If you take any ideal that's not the zero ideal, then the ideal is the whole algebra. So for VOAs over a ring, that's not the right thing to do. It's too strong. What we should say instead is that it will be simple if every proper graded ideal intersects the weight zero component non-trivially. Okay, so if you were to, let's say R was, say, a domain, and then you pass to the fraction field, then this would reduce to the usual notion of simple. If R is a field, this is the usual notion, because then you'll have a constant in there, and then that will generate everything. But it's important that we make this distinction, because there are many situations where you can have an ideal of the ring, which is not the whole ring. Let's say I have a proper ideal of R, and then I can take the graded ideal that's generated by I. If I think of R as being isomorphic to the degree 0 or weight 0 piece, then IV will be the ideal generated by I. It's the I linear combinations of everything in V. And I can quotient by this ideal. And this may not actually be nothing, because at the very least, the weight 0 piece is R mod I. And if I is a non-trivial ideal in R, then R mod I will be non-trivial. So this actually is very important, that simple means this. And a VOA can be simple, but it's possible that when I do this quotient and I consider this to be a VOA over R mod I, this is no longer simple, and this acquires a VOA ideal that you didn't see before. Okay, so today I don't actually need this, but I'm going to need this on Wednesday. So what I want to say is that there are two very different applications of vertex algebras over rings that I'm going to talk about. So one of them is what Thomas already talked about, which I'll call deformable families. So these are vertex algebra where you can take a limit. So I'll say this slightly differently, but it's equivalent to what Thomas was saying, that these are vertex algebras that are defined over a ring of complex rational functions of degree at most 0 in some formal variable kappa. And the poles are along some prescribed set. So many vertex algebras have this property, and I can take the limit as kappa goes to infinity, precisely because the degree as rational functions is at most 0. So if the degree is exactly 0, then I might get something non-trivial in the limit. If the degree is less than 0, then it's going to go away. And there's some set of poles that we have to stay away from, and often the limit has a better structure. So this is the type of example that Thomas already illustrated why it was useful to be able to work over such rings. And then the other example that I'll talk about next time is vertex algebras that I'll call universal objects, that are defined over a ring of functions on some variety. Maybe I parameterize the variety and it's polynomials over several variables, or maybe I leave it in a coordinate-free way with a certain maximality property. And these are useful for classifying vertex algebras. And so we'll see next time why this is useful, because the methods of my talk are sufficient often to find generators for vertex algebras of interest, maybe minimal strong generators. But then you really want to know, if I have vertex algebras that come from different worlds that have the same generators, are they isomorphic or not? And that's typically a hard question to answer, but that can be answered without doing explicit OPE calculations using this notion of classification by generating type. So that's why these will be useful, but I'm going to talk about that Wednesday. Okay, so deformable families are, well, I think I'm going to skip this example because Thomas already did such examples. So I wanted to give you an example before I state what it is in general. And the example, maybe I'll go through this very quickly, is an affine vertex algebra. So let's say G is simple Lie algebra of, say, dimension n. I fix an orthonormal basis with respect to my normalized killing form. And then with respect to this basis, the OPEs look like this. So because this is orthonormal, I have a K here. This is a delta ij, and then I have X of the bracket appearing as my first order pole. So I take a formal variable, which satisfies kappa squared equals K. And I take the ring of complex rational functions in kappa of degree at most 0. And here I only need my possible pole set to be 0. Sometimes I have to have more possible poles, but here I only need pole 0. And what I do is I take a vertex algebra that I'll just call V with coefficients in this ring F, which has generators. They look the same, except that I call them A xi rather than X xi. And what I do is here I only have a delta ij, here I have a 1 over kappa. And so Thomas had essentially the same thing with slightly different language. If K is non-zero, then I have a surjective map from this vertex algebra over this ring to VKG, where I send the generators here to 1 over root K times the generators for the affine vertex algebra. And the kernel of this map is kappa minus root K V. So in other words, if I set kappa to be 1 over root k, then this gives me an isomorphism of vertex algebra. So when I do this quotient, I mod out by the ideal kappa minus root k. That means mod out by this ideal, set kappa equal root k. Then I get exactly vkg. This works whenever k is non-zero. So the important property here is that if you look at this OPE, now it's meaningful to take the limit when kappa goes to infinity, because they're all, this is a constant and this is 1 over kappa. So when kappa goes to infinity, this term goes away and this survives, and I just get a Heisenberg algebra. So I think I'm going to skip this because Thomas already explained this, but the limit is isomorphic to the rank n Heisenberg algebra. And so in a very general setting, let's say that k is some subset of the complex numbers. This is going to be my pole set. It's at most countable. And I consider the ring of rational functions where the degree of the bottom is less than or equal to the degree of the top. So these are rational functions of degree at most 0, such that the roots, possible roots lie in k. So there's a prescribed pole set. The deformable family will be a vertex algebra defined over this ring. You can specialize whenever k is not one of these poles that are not allowed. I should say when root k is not in here. This is also a typo. This should say when root k is not in k. Then the infinity, the limit is well defined. And the main theorem that's important here is, the reason why these are useful is that from the purpose of understanding strong generating type, you can understand the limit. So strong generators for this limit will give rise to strong generators for the family bk for generic values of k in a very general setting. Okay, so let me just say a few words about W-algebras. So I won't, for orbifolds of W-algebra. So this is less important, so I won't say quite as much about this, but if we have a W-algebra, WGF for some superalgebra G and some nilpotent F, Thomas already explained to us why the limit is a generalized free field algebra. And we also know that if we take the orbifold of the limit under some group, if you have a group action on the W algebra, it will induce an action of the group on the limit. We know that the limit is strongly finitely generated. So there's one subtlety, which is the statement that limits commute with taking G orbifolds, in the sense that if I first take the orbifold of the W algebra, then the orbifold itself is a deformable family, and the limit of that coincides with the orbifold of the limit. So the process of taking orbifold and taking limit commute. That's true, and it's not that difficult to prove, and it's a consequence of the fact that the W algebra admits a nice filtration. It's not the canonical filtration of Lie, it's a good increasing filtration. So the existence of such a filtration makes it possible to show that orbifold commutes with limit, and therefore we get the first theorem that I stated at the beginning, which is that orbifolds of W algebras are always strongly finitely generated. Okay, so cosets are a little bit more complicated. So I'm going to spend the rest of my talk on cosets. So first of all, what is the coset in general? So suppose that A is a big vertex algebra, V is a subalgebra. The coset of V and A is the set of all elements of A, which commute with everything in V. So that means that if you write this bracket, this is now a super bracket. So right, it depends on whether these elements are even or odd, but you can always assume that they're homogeneous, take the super bracket. These things vanish on the nose. That's always a vertex subalgebra of A, and I'll call that C. So it has some nice properties that if A and V have Virasoro elements, LA and LV, then this coset has Virasoro element LC, which is the difference of Virasoros. So in particular, if you take the sum of the Virasoro on V and the Virasoro on C, you get the Virasoro of A. So that means that this is a conformal embedding, typically. So this is a useful construction because the various features of the representation theory of A they're very closely connected to representation theory of these two factors. Okay, so the setting that in general, it's very hard to analyze these. So I want to focus on the case where V is an affine vertex algebra. So not just any old subalgebra, but an affine subalgebra. So I'm going to call these affine cosets. Okay, and A is also going to be some vertex algebra where the structure constants depend algebraically on K. So here I have VKG, and this is supposed to be for generic K, or even thought of as over the ring of functions in K. And AK should also depend nicely on K. So the typical examples that we can analyze using our methods are when AK is some larger affine algebra, or some W-algebra, or some free field algebra, or tensor product of such things. Any tensor product of such things you can handle using these methods. Okay. And so I need some hypotheses for A. So it's useful to axiomatize the properties that it needs, and then the examples we need to check that it satisfies these axioms. So I want this AK to come from a deformable family, meaning that there's some vertex algebra, I'll call A, without writing a K down. It's defined over some ring of rational functions with poles in some set of degree at most 0, such that when I do this specialization, I mod out by this ideal. In other words, I set root kappa to be root K, then I get AK for all but the root K's in my pole set. So typically my pole set is very small, and this is for most values. Okay, and then remember, I defined a minute ago that this VKG comes from such a deformable family. So I want this map, AK is supposed to have an action of the affine algebra, so I can take its coset. I want that embedding to be induced by a map of deformable families. Okay, so this is typically the case. That's not much of a requirement. And then the last thing that I want, well, there's sort of two things, is that when I take the limit of A, so A infinity is supposed to decompose as the limit of this, V infinity is the limit of the V part, the affine vertex algebra. So this actually becomes a tensor product in the limit. V infinity was just a rank n Heisenberg algebra, tensored with some other subalgebra that I'll call A infinity. For the moment, I don't care what this is, but just that even though for finite K, this typically does not appear as a tensor factor, in the limit, it does appear as a tensor factor. It may seem to be a strange requirement, but it holds in all the examples that we care about. If this is the case, then this action of little g on A is going to integrate to an action of a connected Lie group G. I'm sorry, no, this is one more requirement that we need in general. We need that the action integrates to an action of a connected Lie group. And of course, it's enough that A decomposes into finite dimensional G modules for this to happen. So we assume that A decomposes into finite dimensional G modules, and therefore we can integrate this action. Those are the axioms that we require. Under these circumstances, there is a general statement that says two things. So so first of all, this coset regarded, if I take the coset of V inside A at the level of deformable families, the coset itself is a deformable family. Something is required to show that that also is a deformable family. And that when I take this quotient, I set kappa to be root K, then I get this honest coset. So CK was the honest coset for some finite value of K. That coincides with the specialization of this deformable family C for generic values. And so one thing which is a little bit subtle is that I may have to throw out more denominators than I had before. So I had A was a deformable family with some pole set. I may have to increase the pole set for this to happen, but I can do that. It's still most countable. And then I get this statement. And the second statement is that this A tilde, right, that was my other tensor factor when I passed to the limit. I had Hn and A tilde. That has an action of my group, and C infinity, what is the limit of this deformable family? It's a deformable family, so it has a limit. That, it's not obvious, but it must be shown that that coincides with the coset of the limit of the affine algebra inside this limit. Well, that's just the coset of the Heisenberg inside Heisenberg tensor this. When I take this coset, the Heisenberg go away, and it just becomes this G orbifold of this A tilde. So in other words, taking the limit doesn't completely commute with taking coset. It almost commutes with taking coset, but I have to throw in this orbifold as well. I have to also take G invariant, and then it commutes. So in particular, a strong generating set for the orbifold will give rise to a strong generating set for this coset generically. And this will, first of all, this works even if I don't know anything about this A tilde. So because I've done this axiomatically, I haven't told you that A tilde need be something that we can analyze, but simply this statement that you can analyze the generic behavior of the coset by passing to this orbifold. The other thing is that I did this for simple G. Well, maybe I didn't say that, but you can do this for simple G, but you can also do this for reductive G. And also it works for OSP12N. So if you have something which is a direct sum of reductive and some copies of OSP12N, the same procedure also can be carried out. So you have a way of studying cosets by passing to orbifolds. Okay, so in the setting of W-algebras, let's say that AK is now a W-algebra for some simple Lie superalgebra and some even nilpotent. And then I have the full affine subalgebra. And now suppose I take a reductive Lie subalgebra of A of some dimension, say n, and then I take the corresponding affine subalgebra. So remember, there was a level shift for A. There may be another level shift for embedding the affine Lie algebra of B in here. And right, this also, if B is reductive, there may be different components, and you may have different standard level with respect to different components. So maybe you have to pick a bilinear form and then do this with respect to that form. So I just wrote this as an L. So you have to check that all the hypotheses hold in these cases, and that in particular, this W algebra will decompose as a sum of finite dimensional B modules. So if this is the case, then the action of this reductive Lie algebra will integrate to an action of a reductive Lie group. And we know that this limit is a tensor product of free field algebras of standard type. That's what Thomas showed us at the end. So what it means is that the limit of this W algebra, so in Thomas's talk, he called this W free. This is exactly the same thing as W free, but I'm just using different notation for it. This will now decompose as some W tilde, which itself is a free field, tensor product of free field algebras times H of n. This H of n is the limit of the affine piece. That was the one that came from my VLB. In the limit, B had dimension n. So this is a big tensor product. One of the tensor factors is Hn, and then there's something else. And then the consequence of this is that the coset will be a deformable family. This is this affine coset for this reductive Lie subalgebra. Its limit will be isomorphic to this B orbifold of W tilde. And now I'm in the setting where I know that this is strongly finitely generated. Therefore, this CK is strongly finitely generated. And this particular holds for generic values of K. Okay. So as I said, at this level of generality, it's not very constructive. We have to be able to say what this looks like for this to be useful in any sense. But what I want to do at the end is carry out an example, which is sufficiently nice that you can carry this out and give an explicit minimal strong generating set for this. And this will be one of the examples that we need for the triality story that we're going to talk about on Wednesday. Okay, so any questions about this general story first? Okay, so I'm going to look at the small hook type W algebras that Thomas talked about, except that I won't do the super case. I'm going to do the even small hook type W algebra. So it's quite similar. So remember that nilpotent elements of SLN correspond to partitions of n. So I'm going to take the partition little n plus big N. I want little n to be greater than or equal to 1, so that SLN plus M is SLN plus GLM plus this module plus this module, where this is Cn is the standard representation of, this Cn is the standard module for SLN. Cm is the standard module for GLM, and then these are the duals. Okay, so you can decompose SLN plus M in this way. And I want my nilpotent element, I'll denote by Fn comma M, to be the one which is principal in SLN and trivial in GLM. Okay, so the in Fnm corresponds to the hook type partition. N is a big block and then a bunch of small blocks. Okay, so that's why I call this a small hook type W algebra. And it's convenient to work with the shifted level rather than the actual level. A lot of formulas become better if you pass to the shifted level. shift by the dual Coxeter number of SLN plus M. So I'm going to write psi is K plus N plus M. And W psi NM is going to be this W algebra. Okay? And so this generalizes some examples that are familiar. So if M is 0, what does that mean? That means that there's none of these small bits. I just have the this big block. This is just the principal nilpotent element. So this just becomes N plus M is N, and this becomes W psi minus N SLN. This is my shifted level for the principal W algebra. If M is 1 and N is greater or equal to 2, then what does this block look like? So that's it's almost principal, but there's one small block. So this is the subregular nilpotent. This becomes the subregular W algebra. If N is 1, which means my long block is really just a trivial block, then this is just the trivial nilpotent. So this is an affine, this W algebra is just an affine Lie algebra, affine vertex algebra for SLN plus 1. And the last one is, suppose that N is 2. So I have one very small non-trivial block, it's just height 2, and then all my other blocks are trivial. That's the minimal nilpotent. And this becomes the minimal W algebra. So this family of examples generalizes some familiar ones. The affine subalgebra, so this vertex, this Lie algebra A, the thing that commutes with that nilpotent. Well, I take the nilpotent and then I expand it to an SL2. The thing that commutes with it is exactly the GLM. Nothing in SLN commutes with it, but the GLM does, and that's it. So the affine subalgebra is an affine GLM, which is just a Heisenberg tensor in affine SLM. And this is my shifted level. So if psi was my level, my shifted level for this one, this becomes the level of the affine vertex algebra. Okay, so the strong generating type, it's similar to what Thomas explained in the case of the superalgebra. So for the decomposition of SLN with respect to the principal nilpotent, I have a bunch of SL2 modules that are different degrees, and each one of these things, I have ones of degree of dimension 3, 5, 7 up to 2n plus 1. So these give rise to fields of weights 2, 3 up to n. And those are invariant under GLM. And then I also have two M fields. I'll call them G plus or minus I running from 1 to M. And they have conformal weight n plus 1 over 2, and they transform under GLM as Cm plus Cm star. So the standard representation and the trivial. Those are all the generators for this vertex algebra. And the thing is freely generated by those. Okay, so now let me consider I'm going to just consider the case where M is greater than or equal to 1, because otherwise there's nothing to do. We want to consider the affine coset. So if the thing is the principal W algebra, then affine coset, we don't do anything to it. So M will be bigger than or equal to 1. So what does the free field limit look like in our language before? So when I take n to infinity, I'm going to call this W infinity, but that's in Thomas's notation W free. Well, there's a piece which comes from the affine part, right? The affine part was a GLM. And so when I pass to the limit, it becomes a Heisenberg of rank m squared, simply because the dimension of GLM is m squared. Okay, so I have an O even m squared 2. That's just a standard Heisenberg of rank m squared. And then I have something else, some complement that I'll call W tilde. Okay, and this, as I said, this HM squared just comes from the affine part. Now, what does the W tilde look like? Well, it's a little bit different depending on whether n is even or odd. And the reason for that is that these generating fields are either half integer dimension or half integer weight or integer. So if n is even, that means n plus 1 over 2, well, n plus 1 is odd, so that means that n plus 1 over 2 is half integer. So if it's half integer, the only difference you see with the part that comes from the G plus or minus I. So the field of weight 2 gives me an O even 1, 4. The field of weight 3 gives me an O even 1, 6, and so on. All these pieces, they're all rank 1, and they just come from these fields I running from 2 to n that come from the SLN part. Okay, so I have a bunch of these things where the heights of the poles are increasing, but they're all O even type. And then the last thing is an S even M n plus 1. So why do you get this? Well, S even is the one where the fields are even, but the conformal weights are odd. So it has to be symplectic type. So the G plus and the G minus are going to give me my two M fields. And so S even M, there's actually two M fields. There's the because I have symplectic basis. And this tells me, this thing over here is the height of the pole, which is twice the weight. Well, the weight was n+1/2. Twice that is n+1. That's what the pole is. Okay, so that's why I get S even m n+1. Okay, now if n is odd, this W tilde, the first bunch of them are the same. The fields and weights 2, 3 through m give rise to all these O even type algebras of rank 1. But then the one that I get from the G's, well, n is odd, so n+1/2 is even. Okay, so it's got to be an O even algebra. The generators are even and the poles are even. And so the weight is n+1/2, so the pole is height n+1, and then I've got 2m of these fields. Right, this one was an orthogonal basis, so I had to write down 2m rather than m, even though in both cases I have a total of 2m fields. Okay, so this is what I just explained. The O even 1, 2 i's, they come from these generators, and these G plus or minus i's, they generate an S even in this case, and they generate an O even in this case. There are no odd fields in this problem. Okay, so now let's consider the coset. So the coset was, I want to take the coset of this GLM inside this W algebra. And so the general result says that what I need to do is pass to W tilde GLM. Remember the W tilde was all this stuff together with this last thing, but I throw out the affine part. Right, I just need this W tilde part. So W tilde GLM. And the coset generically will have the same strong generating type as this orbifold. Okay, so I want to analyze this orbifold. And so this is an example where you can do it because the invariant theory is nice. So the first observation, remember, was that this GLM acts trivially on each of these factors. The fields and weights 2, 3 up to n are GLM trivial. So when I take GLM orbifold of this whole thing, it doesn't do anything to this first bit. It only acts on the last bit. So I have to just understand F GLM. And F is either this S even or O even. Okay, this other stuff is just going to come along for the ride. Okay, so O even 1, 2i has one even generator of weight I, right? The pole is 2i, but the weight is I. So this bit of it, this has weight 2, this has weight 3, this one has weight n. So this bit of it will give you, this will be of type W2, 3 up to n. Okay, so what remains is to understand the S even GLM and the O even GLM. So let's start with the S even GLM. Okay, so remember our generators. So this was symplectic type. So I have the symplectic generators, A1 through AN, B1 through BM. And they have weight n+1/2, right? And the weight is odd because n is even here. And the non-trivial OPE is between an A and a B. And the height of this pole is twice the weight. It's negative quantity n+1. So notice that this GLM action, there's one way of embedding GLM in the full automorphism group SP2N such that the standard representation for SP2N decomposes as CM plus CM star under this GLM. So that's what we do. So the A's decompose as CM and the B's decompose as CM star. That's how GLM acts by automorphisms. That's how we embed it in the automorphism group. Okay, so what we need for this problem is the invariant theory of GLM. And so the invariant theory of GLM says that if you pass to the associated graded, then the generators are quadratic and the relations are determinants, n+1 by n+1 determinants. And so it's not difficult to check that it's a little bit of a process, but you write down all the quadratic generators, then you eliminate some, and then you use the same procedure that we had for analyzing the free field algebras under full automorphism groups to truncate to get a nice finite set of generators. So there are some fields, I'm going to call them WJ. They're AJ times the J, sum over I of AI times the Jth derivative of BI. J runs up to some point. And this is all a consequence of facts of invariant theory, where these WJs, well, first of all, what is the weight? It's going to be J plus the weight of two of these. A and B both have weight n+1/2. So I've got n+1 plus J. That's the weight of this thing. And so the generating type of this thing is W n+1, n+2, up to whatever this quantity is plus n+1, which you rewrite in that way. So it's a lot of notation, The point is that it starts with n plus 1 and n plus 2, and it goes up to some point. The reason why it goes up to some point is that I first do this going to infinity, and then I consider relations that come from determinants, and I have to analyze these quantum corrections because the determinant doesn't vanish. The one of lowest weight, the relation of minimal weight, is exactly of this weight, which you see from the form of Weil's theorem. And you have to check that it actually gives rise to a decoupling relation. You have to analyze the quantum correction. And this is a complicated process using recursions that govern these corrections, but you can carry it out. And this is the result. This is the type. So what do you get from that? I don't think I wrote it down, but so I should have written this down because we're going to need this next time. So we have to put this together, that the first bit of this comes from, I have W2, 3 up to n, and now I've got W n plus 1, n plus 2 up to here. So the upshot is that you have generating fields and weights 2, 3, all the way up to this quantity, n plus 1, n plus 1, plus 1, minus 1. And maybe I'm a little bit out of time, so maybe I should skip. This is my last slide. The same thing works for the even orthogonal case. So maybe I'll skip the details here. It's exactly the same idea that when you want to analyze this, again, it becomes a GLM invariant theory problem. The generators are quadratic, the relations are determinants. You can analyze the quantum corrections, you get the generating type. Both of these algebras, it turns out, whether n is even or odd, have the same generating type. So this is where I want to end today. So the point here is that we have a general machine for computing strong generating type, or at least proving in general that it's finite, and then in some examples like this, explicitly showing that it's of a certain generating type. So that in of itself is not particularly useful because it's a far cry from showing the two algebras have the same generating type to showing that they're isomorphic. Our goal is to prove that things that are not obviously isomorphic actually are, some of these things that are predicted in physics. So we're going to have to classify algebras with this kind of generating type. So the generating type will be 2, 3, 4 up to something. So that means minimal generating set consisting of one field in each of those weights. So there is a machine for doing this that I'll talk about next time. And with very little data, if I have two algebras with some generating type, there's a way to tell whether they're isomorphic without actually knowing their OPE algebra, which is utterly impossible most of the time. So this method combined with classification of VOAs by generating type yields non-trivial isomorphisms. That's the thing to take away. So that's all I wanted to say for today.
Oh, thank you very much. Let's thank the speaker. So are there any questions?
So if I may ask about the first half of the talk, so you had these ON orbifolds of maybe n copies of your Heisenberg algebra or so. Do you know? I mean, do you know something about how representation theory looks like? So there's twisted sectors, so there's a module categories and so on. Is there at least on this level something known?
Let me think. So you mean I personally, I don't know that much about. So in some sense, the represent. I mean, in some sense, let's say that you want to consider just the representations that are seen by the W-algebra, the ordinary modules that are n-graded. I know that the irreducible ones have top degree 1. I know that they all are highest weight modules in some sense. I know that the highest weights are parameterized by the spec of some ring. The W-algebra is commutative, so you take spec of this ring, you can. So in general, that's very difficult to compute. It's an interesting problem to describe this ring. So it's known for H, in the case of one Heisenberg, the modules are classified. And the ring is something like, it's got two generators you mod out by some relation, but the ring is a non-reduced ring. So you have to take the points in this variety. So this is written down explicitly in Dong Nagatomo's paper, and they use it for various things. Like it's a starting point for studying the representation theory of orbifolds of Z2 orbifolds of lattice VOAs. So beyond this example, I know something about it also for 2 copies, because 2 copies of the Heisenberg algebra is a lot like the parafermion algebra. So if you take the parafermion algebra, so that's take SL2 and take the Heisenberg coset of SL2. That's a parafermion algebra. If you pass to the limit, then there's not algebra. First of all, it's of type W2, 3, 4, 5. So I'm sorry, no. What I said is not exactly right. It's the orbifold of the parafermion algebra. So H2O2 is just a U1, is an orbifold of a parafermion algebra. So those modules are also classified. There's some recent work of Jiang and Wang in China where they classify the modules for parafermion algebras, for orbifolds of SL2 parafermion algebras. And also you can easily say what this variety is and write down what determines highest weight vectors. So in general, I don't know. It's a very interesting question to write down the relations that cut out this variety. So I know that you know how many generators there should be, and then some relations you can write down. But somehow classifying the modules in the most general sense, I think amounts to describing this Joux algebra. But then there are some of the modules appear in HN because you have this duality between the ON modules and the HN-ON modules that appear in HN. So that's not all the modules, but it's some nice class of them. So I think that more generally, if you have a module for HN, then you have a decomposition as modules for ON. And there will be certain nice ones that appear that are in duality. But beyond that, I don't know. And twisted modules, I haven't thought about. I know there's a theory of twisted modules for automorphisms. They're not finite, but I don't actually know much about it.
Other questions? So if not, let's thank the speaker. So we'll resume tomorrow at 6 p.m. Moscow time.
So we continue, yes.
Yeah, so we will continue tomorrow.
Mm-hmm.
At the same time as today.
Okay, so thank you.
Thank you.
Thank you.
Thank you very much.